This is the third week in the module in sustainable energy, and this week we'll cover climate change and air pollution, the specific topics. First of all, climate change science, basics of climate change. We'll talk about carbon and methane impacts and cycles. The third lecture will be on climate impacts. The fourth will be on how to calculate carbon emissions from energy. And the fifth lecture will be on local air pollution, which is distinct from climate pollution. And in this first lecture of the third week, we talk about the basics of climate science. So this was a sample of magazine covers in September 2019. Thousands of people marched for general demonstrations on climate change. For example, in Cork, in our city, there was very, very large demonstrations throughout the city. 4 million people marched worldwide, and these were to coincide with the UN General Assembly and Summit on Climate Change, and a huge week of media attention focused on the need to mitigate climate change. And the reasons are stark, really. This was a fantastic image from from Nature that week, and it shows the scale of increase in CO2 emissions by country since 1900. This is the year 1900, where we emitted around 2 billion tons of CO2 that year. And in the 120 years since, we're now burning 36 billion tons of CO2 every year. Now China is the main emitter of CO2, but basically it's every country in the world, and the scale is stark. We're not slowing down as fast as we should be. This lecture gives you a quick history of climate science, how we first discovered that humans are causing warming of the atmosphere, what is the physics and chemistry behind that. The first scientist to explain the greenhouse effect, which we now know is the cause of global warming, was Joseph Fourier, who you might know from other coursework. Fourier is best known for the mathematical techniques he developed in his analytic theory of heat transfer, and in the past 2 centuries since he began working, his methods really evolved into major subjects, including harmonic analysis, which has widespread applications in number theory, signal processing, quantum mechanics, weather predictions, and many other fields. So Fourier's equations are used widely in physics, in maths, in chemistry. But Fourier was also the first person to study the Earth's temperature from a mathematical perspective. He examined variations in the temperature between night and day and between summer and winter, and he concluded that the planet isn't as warm. The planet is much warmer, actually, than a simple analysis might suggest. So he calculated that it should be much colder if all the incoming radiation from the sun were the only warming impact. And his idea was that the Earth's atmosphere acts like an insulator, it's like a blanket. And this is the first formulation of what we now know as the greenhouse effect. However, he didn't use that term greenhouse effect. That first appeared in the work of the Swedish meteorologist Ekholm around 1900. But around that time, then another major physicist, John Tyndall, who has obviously very strong Irish connections. He was born in County Carlow, and his name lives on in legacy in different institutes that we run here in UCC. He conducted a series of experiments in the 1850s to measure precisely how infrared radiation is absorbed by gases. So he tested several gases and vapors and found that while some pure elements like oxygen and nitrogen have little effect on temperature absorption, more complex molecules actually absorb heat strongly. So Tyndall showed that water vapor, carbon dioxide, ozone are strong absorbers of heat radiation, and he speculated how changes in water vapor and carbon dioxide are actually related to climate change, and this is obviously now what we call the enhanced greenhouse effect. He realized that the strongest effect was from water vapor, and his quote was that without water vapor, the Earth's surface would be held fast in the iron grip of frost. Very poetic. The next major scientist in this kind of broad history of climate scientist was Svante Arrhenius, who was Swedish, and he was the first Swedish Nobel laureate, and he won the Nobel Prize for Chemistry in 1903. He was really the founder of the science of physical chemistry. He developed a theory to explain ice ages, because by then they knew the history of different ice ages, and he used the basic principles of physical chemistry to conclude that atmospheric concentrations of CO2 will increase the Earth's surface temperature through this greenhouse effect. And actually these calculations led him to conclude that burning fossil fuels and other combustion processes at the human scale are large enough to cause a warming effect. So those conclusions obviously have been extensively tested and proved, and this is the core of modern climate science. But what none of these physicists and scientists foresaw was how actually fast and how quickly the use of fossil fuels would grow. So see this chart here, which shows CO2 emissions again from the time of the Industrial Revolution. In 1900, at the time of Arrhenius, the deliberate burning of fossil fuels was entirely almost coal-based, which was driving industrial engines. But since then, population growth, economic growth, and the way that we've exploited many fossil fuels means that we are many more times emitting many more times the level of CO2 that we were at that time. That has very important implications for the Earth's atmosphere, and this is the basis of the greenhouse effect. So essentially, the greenhouse effect explains why the Earth's temperature is a comfortable 14, 15 degrees, rather than the minus 18 degrees it should be if we were losing all that radiation to the atmosphere. So temperature of the Earth is as a result of the balance between energy coming from the sun and leaving as radiation and as heat. So about half of the energy here, we have solar radiation from the sun. The atmosphere allows most of the solar radiation to pass through the atmosphere. Some of it is reflected from clouds and from the Earth's surface. That radiation is just reflected back. But about half of the energy coming from the sun is absorbed in the form of solar radiation, and half of it is reflected back. But some of that solar radiation is absorbed by the Earth's surface as heat. So it goes from solar radiation to heat, and it warms the Earth's surface, water, the oceans, and it warms the atmosphere. Part of this heat is radiated back into the atmosphere, and the temperature that we feel in the atmosphere is a measure of that heat energy that's reflected back. So some of that heat energy here is reflected back. It's lost to outer space. Some of that heat energy is also called infrared radiation, and a lot of that infrared radiation is lost to the outer atmosphere, lost into space. But not all of it is lost. Some of that infrared radiation is absorbed and re-emitted by the greenhouse gas molecules, and this is where the greenhouse gases in the atmosphere really come into play, because these greenhouse gases are essentially they allow solar radiation to pass through, but they absorb a lot of the infrared radiation. And here's just a restatement of that greenhouse effect. So radiation from the sun is in the form of ultraviolet, visible, and near-infrared radiation. So this is the electromagnetic spectrum, and we get radiation from the sun in this form. So in these white arrows, this radiation hits the Earth in the form of these different forms of radiation. About 26% of that energy is reflected back into space. And 19% is absorbed by the atmosphere, and the remainder is absorbed by the surface of the Earth, which heats the Earth. So as the Earth heats up, it re-radiates out that energy in the form of lower infrared range radiation, so longer wave radiation, which is heat, and the lower frequency radiation is more readily absorbed by the atmosphere, so that heats. So basically, the greenhouse gases are readily absorb that low frequency radiation, and then the atmosphere then re-radiates that heat down back towards the Earth, and that causes more radiation back up, and that's where this equilibrium temperature that the Earth has of around 14, 15 degrees, as I said. So just to restate, energy emitted by the sun is characterized by short wavelength radiation, mostly in the visible wavebands, so that's why we see light. And energy radiated from the Earth is mostly in the lower frequency bands of the longer wavelength infrared radiation. That's mainly heat, what we experience as heat in the atmosphere. So what happens when there's higher greenhouse gases in the atmosphere? That affects this equilibrium temperature. So importantly, this crucial point is that this equilibrium temperature depends on the ability of the atmosphere to absorb low frequency infrared radiation. So we absorb more heat in the Earth, so that's when there's more ability to absorb, we have a higher equilibrium temperature, and the greenhouse gases such as CO2 increase the absorption rate, and that is what leads to higher temperatures as a result of CO2 concentrations in the atmosphere. So what are greenhouse gases? They are naturally occurring gases in the atmosphere. The most important ones are CO2, carbon dioxide, 1 carbon and 2 oxygen atoms per molecule, water vapor, that's just H2O, methane, which is 1 carbon and 4 hydrogen, CH4, and nitrous oxide, N2O, ozone, which is O3, 3 oxygen molecules are also there, and they're collectively termed greenhouse gases. So these gases, to restate, absorb the outgoing energy emitted from the Earth's surface, radiation, heat, and re-radiate a significant proportion of that back to the Earth, warming the lower atmosphere. And this process has been in place since the development of the Earth's atmosphere, called the greenhouse effect, and that's what makes our Earth such a nice place to live, that mainly temperatures range on the whole between 0 and 30 degrees, which makes it habitable for life. Liquid water is common, and life is pretty good. But what happens when that goes out of balance? Well, anthropogenic sources of greenhouse gases, GHGs, are shown in this chart. Anthropogenic means comes from humans. There are natural sources of greenhouse gases in the natural carbon and methane cycles in the next lecture, but these are sources of greenhouse gases that come from people, from humans. You can see here the blue ones here are as a result of our energy consumption. The dark blue is from energy combustion from countries. This is from international transport, aviation and shipping, and then other non-energy CO2 from agriculture, things like that. These brownish ones are CH4, that's methane, coming from energy, that's the extraction of fossil fuels. So CH4 is, by the way, also methane. It is methane, and it's the same molecule as natural gas. So we can either burn natural gas to create CO2, or it's released to the atmosphere as CH4, and that's a different greenhouse gas. So this is the sort of energy-related, methane-related greenhouse gas. And then CH4 from agriculture, we hear a lot about that in Ireland. I'll come to that in more detail later. We also get a lot of methane from waste, from rotting, decomposing things. And then we get some nitrous oxide as well. Land use change emissions are also very significant, and that's when the natural carbon cycle in terms of forestry is disbalanced, basically when the carbon sinks, which are forests, are off balance, and carbon is released from land use, from forestry, from things like from decreasing the carrying capacity of peat bogs. And you see here that all the different sources of greenhouse gases are stacked against each other, and you might ask, how do we compare, say, a ton of CO2 with a ton of methane, with a ton of N2O? We gather them all together in what we call CO2 equivalent. So we make an equivalence between the other greenhouse gases, CH4, nitrous oxide, F gases, and so on, and we equivocate them to the equivalent warming potential of CO2. We use this metric called global warming potential, GWP. And the global warming potential was developed to allow these comparisons between the global warming impacts of the different gases. Each different gas has a different characteristic in terms of how strongly it absorbs radiation, so its heating ability, and also its atmospheric lifetime, because some molecules last for a long time in the atmosphere and some break down very quickly. So these different characteristics of gases are very important for how they heat the atmosphere. So the GWP metric measures how much energy the emissions of 1 ton of a gas will absorb over a given period of time relative to the emissions of 1 ton of carbon dioxide. So the GWP of carbon dioxide is by default 1 because we measure every other greenhouse gas against CO2. So if a gas has a high radiative forcing means how much it heats, but a short lifetime, so if it decomposes in the atmosphere, it will have a large GWP on a 20-year scale, but a small one on a 100-year scale. And these are some different example global warming potentials for different greenhouse gases. And what we're most interested in here is methane. So over a 20-year period, 1 ton of methane has an 84 times the heating impact of CO2. But if you measure it over a longer time period, because methane lasts for a much shorter time in the atmosphere, the warming impact is not as significant. So over a 500-year period, over 5 centuries, 1 ton of methane has about 7 or 8 times the warming effect of 1 ton of carbon dioxide. Carbon dioxide has a half time, so if 1 ton of carbon dioxide is released to the atmosphere, then half of it will still be there in about 90 years. So it has a much longer time in the atmosphere than than methane. So if a molecule has a longer atmospheric lifetime than CO2, its GWP will increase when the time scale is considered. And an example there is, CH4. So it has a 50,000-year lifetime, and it has a very strongly increasing impact on climate change. But we still only release that in very small levels. And this CO2 equivalent metric in the last slide is how we create that equivalence. So we have different GWP metrics. So if we use GWP 100, we will we will say 1 ton of methane equals 28 tons of CO2 equivalent. And how is this related to heating of the atmosphere? Because this is something that is of the most importance. That's what we measure in radiative forcing. So radiative forcing, according to the International Panel on Climate Change, the definition is the measure of the influence some factor, one factor might be CO2, CH4, but there's many different factors, has on in altering the balance of incoming and outgoing energy in the Earth atmosphere system. And it's an index of the importance of that factor as a potential climate change mechanism. So in that report, radiative forcing values are for changes relative to the pre-industrial conditions defined at 1750 and are expressed in watts per square meter. So square meter of the Earth, how many watts, remember watts from the energy power units. So how many watts does that effect increase the warming potential? How much extra energy does the Earth absorb for every period of time? And you can see here, this is what the IPCC says is the radiative forcing relative to 1750, and CO2 accounts for the majority of that here. So for every square meter on Earth, CO2 now increases the incoming radiative forcing relative to pre-industrial levels by 1.68 watts. Carbon CH4 there has a radiative forcing level of nearly 1. It's the second most significant source. Halocarbons, N2O, CO, and all these different greenhouse gases have this effect. There are some effects on the climate which actually reduce the greenhouse effect, and these are mainly to do with albedo, clouds, and pollution. So when there's actually pollution in the atmosphere, it reflects light, and that reduces the greenhouse effect. But basically, here is the estimated total increased radiative forcing of the Earth as a result of all these different factors, and you can see the error bars are fairly significantly high. CO2, the error bars are quite low, but here it's mainly aerosols and clouds that cause the biggest uncertainty. Here are the confidence levels in these net forcing levels. So we have very high confidence in the forcing levels from CO2 and high confidence in these various other greenhouse gases, but we have low to medium confidence in these other effects. What we do know for sure is that there is higher radiative forcing, and that has an impact on the climate. We know that we're emitting greenhouse gases to the atmosphere, and we can actually observe these greenhouse gases in the atmosphere as well. So since the beginning of the Industrial Revolution, the concentrations of most of the greenhouse gases have increased in the atmosphere. We can measure that very specifically with both samples from ice cores mainly is how we measure that. So for example, the concentration of carbon dioxide has increased from about 280 parts per million, that's the measure that we use in pre-industrial times, to 408 parts per million. So here you can see all the various interglacial periods, the various ice ages and so on, from hundreds of thousands of years ago, and we are now way above that in terms of our CO2 concentrations in the atmosphere. And these are rising at about 2 parts per million a year. Here are observations from different observatories. You can see methane as well. There was a pause a number of years ago, which hasn't been fully explained, and the methane is rising again, and various other greenhouse gases, the concentrations in the atmosphere are rising. So Arrhenius was right in his hypothesis that a large part in the difference in the temperature between the ice ages and the warm interglacial periods were to do with greenhouse gases. So the world is far different from it was in the ice ages, and since the pre-industrial period, the proportion of the global total cumulative emissions over the time was primarily land use change, when we were chopping down trees, removing rainforests, and basically bringing agriculture to the whole world. But now, in cumulative impact, the impact of fossil fuels is far greater than the impact of land use change. So concluding slide is a reflection on why the complexities of climate science. You see, it's not as simple a matter as burning 1 ton of CO2 and that leads to warming, which is true, but there's complexities and relationships between greenhouse gases, and these complexities and these different effects meant that it took time to prove unequivocally that CO2 and burning fossil fuels were the main cause of climate change, and to be very precise about those effects. For example, just one sort of complexity, water vapor actually amplifies the effect of other greenhouse gases. There are nonlinear impacts. So a warmer atmosphere also is a moister atmosphere because more water can be contained in a warmer atmosphere. But then water vapor also condenses into clouds in many conditions. And some types of clouds cool, some heat. So there are these uncertainties, and that's why the error bars on the water vapor radiative forcing chart was very high. The uncertainty range was very high, and this causes uncertainty about the exact dynamics of the greenhouse gases. Also, burning fossil fuels and volcanic eruptions release aerosols, which are particles small enough to float in the air. They also carry viruses, by the way, as well as carbon dioxide. And these aerosols warm the atmosphere, but also they cool via shading. So some particles, like aerosols, can have a warming and cooling effect under different conditions. And there are also natural variations in the Earth's climate. So the brightness of the sun varies over time. So the incoming radiation changes over times. And there's internal climate dynamics. For example, El Nino events happen over a cycle of a number of years, and those change the mean temperature of the planet over time, making modeling difficult. And these complexities meant for some time there was doubt about greenhouse warming, and the fossil fuel lobby over the 20th century deliberately fostered these complexities and uncertainties to delay action on mitigating climate change, and that's also unequivocal. So there's evidence that fossil fuel companies kind of seeded uncertainty into these effects. But today there is no legitimate doubt that observations of global warming show that the effect is unequivocal. The Earth is warming, and humans are the main source of that.